Tamimisha. Tamimisha. Tak tahu. Anas. Anas. Can you hear me?
Yes, doctor, we can hear you.
Yes, doctor.
Ayman,
Yes, doctor.
read the question, please.
Question 1A. Define root locus and explain its significance in control system analysis and design. B. Sketch the root locus plot for the system described by the transfer function Gs equal to Ks plus 1 S over S, S plus 2 and S plus 3. Indicate the behavior of the system as K varies from 0 to infinity. C. A unity feedback control system is given in figure Q1C I, the root locus of the system shown in figure Q1C2. The system is operated at 17% overshoot. Determine the following: the dominant poles and the operating gain K at this point. The third pole of the closed loop system for gain K obtained in C1. Next, determine whether the third pole can cancel the closed loop 0, hence it can be approximated as a second order system. The peak time, settling time and steady state error for a unit step input. From the root locus, give your comment on the system stability. And the last one is design a controller that could eliminate the steady state error obtained in C3, but maintaining the same transient characteristics. Validate the new steady state error after the implementation of the proposed controller.
Okay, so this is the plot given. Okay, thank you. So, question 1A. Is the theory, eh? So you can see that our root locus is graphical method. Okay. To analyze what? The behavior of roots of characteristic equation or closed loop poles. Okay. So for controller design, okay, i.e. P, PI, PD, and PID. Okay. So something like that. Okay. You have to compose a paragraph lah. Consists of these all keywords. Can eh? And then the other one is the sketch of a given open loop transfer function, which is GS. GS is K S plus 1 S plus 2 S plus 3. Okay, so we have a system, third order system, and system that one. Okay, open loop 0 -1, open loop pole 0, -2, -3. Okay, so we are required to sketch. Sketch meaning a freehand draw. Okay, real axis and imaginary. And the poles at here, okay, which is 0, -2, -3, and -1. Okay, so far okay. So we have to calculate the, what do you call that? Calculate the sigma A and theta A. Sigma A is the intersection at real axis. This one is the angle of asymptote. Okay, so we calculate sigma A, which is the value of the poles, -2, -3, okay, 0, plus the zeros, and then the number of poles 3, and the number of 0 is 1. So this will give you +2. Okay, so meaning that sorry, not +2, minus. Okay, and then the angle of asymptote, which is 2k plus 1, 3 minus 1, number of poles minus number of zeros. Pi is 180. So you will get 2k plus 1 pi divided by 2. And then since k equal to 0, k equal to 1, okay, so the asymptote for k equal to 0 is pi over 2, which is 90 degrees. And when k equal to 1, which is 3 plus 2 pi, which is 270 degrees. So therefore, the rule locus start from the imaginary axis. There is a poles ended at zeros. Okay, and then the other one is this one. Okay, and then we draw the angle of asymptote. Okay, something like this, angle of asymptote. And then the locus is something like this and goes here. Okay, so dia ada bengkok sikit. Ada curve due to the zeros here. Okay, so what can you say? The stability system is stable. One Faris.
Yes, Doctor.
Or all value of k. Macam tu jawab. Yeah? Boleh eh? Can you answer like that in the final exam?
InsyaAllah, Doctor.
Bagus. Good. Ada response. And then we finish part A, part B, now part C. Now you are given 70% overshoot. Okay, so 70% overshoot. We have to use what do you call that? The graph. Overshoot is 70%, which will give you zeta. Can you look at the appendix? What is the suitable zeta value? Haris Mazlan. Okay. So cos theta equal to zeta. Cos theta equal to 0.491. So theta is inverse cos 0.491, which will give you Haris Mazlan. Tak tahu. Coming. Mashfiq.
60.6, Doctor.
61 degrees. 61 degrees. So in that case, you have to use a protector. Okay. Use protector at 61 degrees at the given question there. 61 degrees. So this is the origin. Okay. So 61 degrees, I think about here lah. Okay. 0.491. So it's about here. The theta is 61 degrees. Okay. Draw the zeta line at theta 61 degrees yields dominant pole. Where? Here, At here. So that is your SD, dominant poles. Okay. So what is the value of dominant poles over there? Shadow? There is student name Shadow. Anas? Dominant poles? Approximate? .9? And the value of the gain over there is how much? What is the gain over there? There. This is the open loop. So S+1, S+3, S+7. S+4. Okay, so you insert S inside here. So you will get the value more or less about 45. Okay. Question number 2 is this one is number 1. Number 2. What is number 2? Yeah. Okay. The third pole of the closed system will be obtained in C1. The third pole of the closed loop system for gain K in C1. Okay, use the gain which is 45. Okay. K 45. Characteristic equation, yeah. What is the characteristic equation? GS is S plus 4K. Okay. S plus 1. Okay. So close loop. Which is plus K S plus 4, correct? So the characteristic equation, okay, is S plus 1 equal to 0. Okay. So use the characteristic equations, okay, and solve for S. Okay, so in this case, S plus 3, S plus 7, plus 45, S plus 4. So you simplify this one, okay, and then you will get the third pole is minus 4.2 pi. Okay, so this pole, the above third pole will cancel out the close loop 0 at minus 4. Okay, so therefore the system can be approximate as second order system. Okay. Third one is the peak time, steady state error, KP, and so on. So the settling time, okay, just take the value of the 4 divided by real, which is 1.18 second. EP is pi divided by imaginary, which is 0.52. Okay. Yes. Then using a final value theorem. Final value theorem. So this system is type what? Lim. The system is type what? Lim?
Type 0.
Type 0, eh? Type 0. So therefore, kita guna KP. Okay. S to 0. KDS. Okay. So K is 45. K is 45. S plus 4. S plus 3. S plus 1. S plus 7. So the KP value is, what is the KP value? Nevin, help me. 45 multiplied by 4, 180, divided by 21. Somebody help me.
8.57.
8.57. Thank you. So the steady state error is 1 over 1 plus Kp. 1 over 9.57, which is
0.104.
Thank you, Miss Lee. Thank you very much. So what is the stability comment? System is always stable for all K value. Then calculate the PI controller. The last one. Haris Mazlan. Haris Mazlan. Tak tahu. One Faris. One Faris.
Yes, okay.
Suggest PI controller for the system. Tak tahu. Tak tahu.
Not sure, Doctor. Ingat.
Apa paling senang? Ahmad Fatih. Ahmad Fatih Salim. Abu Bakar. Suggest. Okay. So that is the PI controller. Re-evaluate steady state error for G overall will give you steady state error 0. Okay? Are you okay? Are you okay, guys?
Okay, Dr.
Yes.
PI controller pun tak tahu ni. Tangkap lah. Miss Lee, can you read question
Yes.
number 2?
Figure Q2A illustrates a unity feedback system with a forward transfer function of a plan having a unit step function input. The open loop transfer function GS is given as GS1 over S plus 2, S plus 5, S plus 20. A controller GS is required to improve the performance of the uncompensated system. The system is operated at 20% of overshoot with the dominant poles given as SD equals to negative 2.67 plus minus J 5.22. 1. Determine the gain K, the settling time TS, and the peak time TP of the closed loop system at the given dominant poles. 2. From Q2A1, determine the new dominant poles. SDN if the compensated system settles 3 times faster than the uncompensated system. 3. Using the new dominant poles, design the PD controller and determine the values of proportional KP and derivative gain KD of the controller.
Sure. Okay. B. Continue B.
A unity feedback system with unit step input has a closed loop transfer function given by Ts equals to 40k over S multiplied with S plus 4 square plus 40k. Design a PID controller using Ziegler-Nichols tuning method and find the values of Kp, Ki, and Kd. The PID controller transfer function is given by GPID equals to Kd multiplied with S square plus Kp over Kds plus Ki over Kd over S.
Thank you. Right. So we move to question 2. Okay. There is no work plot given, just overshoot 20% and dominant poles is given by minus 2.67 plus G 5.22. Okay. Determine the gain key. Okay, determine the gain key, settling time, peak time. So how are we going to do it? How to find the gain key? Khalid? Khalid. I'm coming. Masya ikhwan. Masya ikhwan. Anybody? How to get gain?
Use dominant poles substitute inside
Hmm?
the formula
Which formula?
poles over 0. Then put the dominant poles inside. Then
The,
find the magnitude.
the transfer function is not given.
Uh,
Um,
I thought it is given
in the question too.
the
It is given.
Oh, it is given. I'm sorry.
yeah, it is given. Question
Okay,
2.
sorry. Okay. So it will be S plus 2, S plus 5, S plus 20. Okay, over 1. So you replace S inside here. So you will get K equal to 544. Okay. And then the settling time as usual, 4 divided by real, 4 divided by 2.67. Okay. 1.5 second. And the peak time is pi divided by imaginary, pi divided by 5.22 equal to 0.6. Okay. And then that is question part 1. Part 2. For part 2, the new dominant poles 3 times faster than uncompensated system. New dominant poles. SD new. Okay. Which is the settling time 3 times faster than uncompensated, meaning that new is 1/3 TS. Correct? Okay, so therefore use standard graph. Which is 20%. Equal to zeta 0.45. Okay. TS new is equal to 1/3 TS. So 5 second divided by 3, meaning that it is a 0.5 second lah. That's a new real. So therefore, this is the new dominant pole. Sigma new. Okay. The real part. Which is 4 divided by 0.5, which is equal to 8. Okay. Real new. Okay. Sigma. Then for the zeta is 0.45. Real is equal to zeta equal to minus zeta omega n. Kan? So that's why omega n is equal to 8 divided by zeta, which is equal to 17.8 radian per second. So therefore Tp will be pi omega n 1 minus zeta square. So you insert there 0.1976. So you insert this omega n, you insert this zeta. Okay. So now new imaginary. Okay, new imaginary will be omega n 1 minus zeta square. Okay. New imaginary is omega n. Just now was 17.8. 1 minus 0.45 square. So you will get 15.9. So that's why new dominant poles minus 8 plus minus j 15.9. Okay. So use this, use the SDNU to design PD controller. Okay. So how to design a PD controller? Haziq, Fadilah, how to design a PD controller? Datang. Anas, how to design a PD controller?
Using angle of criteria formula.
Draw first lah. Okay, draw. So let's say this one. Minus 8 plus j 15.9. Can. Then what is the minus 2?
3 poles.
Nine.
-2, -5, -20.
Minus 20. Alamak. Okay, minus 20. Minus 5. Minus 2. Okay. And then you put the 0 somewhere here. Okay. Let's say, well, I don't know where we to put the zeros. I think it's crowded over here. Okay, we can put here. Where to put? Okay, you can
In
put.
between -5 and -20. Guessing.
Okay lah, we put here lah. Okay. ZC, eh? Okay. Then we draw the line. And then calculate the angle. Okay. So let's say this one is theta 3. Let's say this one is theta 2, theta 1. And this one is theta. Okay. So calculate the value. Theta 1. Arctangent. One 0.7 degrees. theta 2 arctangent over 3 theta 3 arctangent so therefore theta 1 theta 3 okay equal to 264.36 degrees minus 180 darjah, so the theta will be 84.38 degrees, okay? Something like that. So
Sir, tangent inverse 15.9 over 2, I got 82 degree, 82.83.
theta 3 tangent wait 15.9 20 minus 8 how much? 20 minus 8
Oh, it's 12.
12 sorry 12
Yeah.
12 sorry so it will be 52.96 okay right so this is your 84 see this one is 15.9 this one is under considerations x this one is minus 8 okay so this one is E so therefore E is equal to 1.57 plus 8 9.57 okay so therefore your ZC is minus 9.57 okay so the GPD okay was K S plus 9.57 okay so this is your PD controller and then you find the GPD for overall okay the gain K use the previous one okay that is question number 2 okay sorry continue okay the K for PD controller was S plus 2 S plus 5 S plus 20 okay so you insert S sama dengan minus 8 plus J 15.9 insert here so you will get 20.296 as the KPD over here okay for Q2B is Ziegler-Nichols okay tuning okay so given open loop transfer function for the key okay design a PID model okay So we find the characteristic equation. Find yes, closed loop transfer function. Then you get the characteristic equation, which is simplified. S cubic inside root width table. Okay. S cubic S2 okay. Then continue 16.5 K 40 K 0 0 0 0. Okay. Okay. This one is the first column. So what is the range of stability? So this one is greater than 0, okay. Greater than 0, okay. So this one must be greater than 0. This one also must greater than 0. So 16, 5K greater than 0. Okay. Which will give you 3.2. And then 40K greater than 0, K greater than 0, equation 2. So therefore the range of stability is 0, K 3.2. Yeah. So what is the K critical? When K is equal to 3.12. Okay. Because use the even equation in root width table, which is 8 S square 40K equal to 0. Okay. K is 3.12. So 8 S square plus 40K, 40 multiplied by 3. So S will be plus minus J4 plus minus J omega. That's why omega is equal to 4 radian per second. Okay. So for Ziegler-Nichols tuning, we have the procedure. Okay. We have the procedure. So we calculate omega u first, which is 2 pi tu. Okay. So omega u is equal to 4. So that's why tu is equal to 1.571. Okay. Then use the table of Ziegler-Nichols. Attach in the final exam paper. Okay. So Kp is equal to 0.6 Ku, okay, which is 1.92. So this one is 3.12 just now. Then Td, Tu over 2, 0.786. Sorry, this is not Td, this is Ti. Td is equals to Tu divided by 8, 0.196. Ki, Kp divided by Ti, 2.44. Kd, Kptd, 376. Then you insert inside the GPID, okay, the KD, KPKDS plus KIKD OS, okay. Insert inside the value, then you get the GPID. Okay, we have a break for 10 minutes. Is it okay? Okay, we continue with question number 3. Lim Yuan King. Lim,
Yes.
can you read the whole question number 3?
Consider a system with a transfer function SGS equal 1 over S plus 4. Determine the analytical expressions for the magnitude and phase of the frequency response of the system. Find the magnitude and phase of the frequency response when the frequency omega equal 10 radian per second. Using the expressions, prove that the gain crossover frequency is approximately 0.2495 radian per second, then calculate the phase margin of the system. A system can be represented in a block diagram as shown in figure Q, question 3b. Rs and Cs are the input and output respectively, and Gs equal S plus 10 over S plus 50. The system needs to be analyzed in the frequency response. Sketch the block plot for the open loop response of the system. For the x-axis, consider 4 decades between 0.1 radian per second to 1000 radian per second. For the magnitude plot, the y-axis can be in the range of 40 dB to negative 80 dB. Label the sketch completely. Figure question 3C1 shows the closed loop system with the system transfer function Gs equal 10, S plus 2, S plus 5. With K equal 1, the both plot for the open loop response of the system is shown in figure question 3C2. Using the plot, find the gain margin and phase margin of the system. Determine the steady state error of the system to be a unit ramp input. Analyze the stability of the closed loop system. Number 4, to increase the range of stability of the closed loop system, the gain margin need to be increased to 30 dB. Using the gain adjustment technique, determine the gain K to achieve the requirement.
Thank you. Right, so we move to Q3A. Okay, so where you are given okay, so as usual, use S equal to J omega. Okay, and then find the magnitude. And find the phase. Okay, so very straightforward. Okay, and then part 2 is given omega 10 radian per second. So the magnitude is 1 over is 9.28. So 20 log G omega. So you will get minus 40.64 decibel. Okay. That is number 2. And the phase, you can put okay, you can do it yourself, okay, using the formula that given here. Okay. Question number 3 is find the gain crossover frequency. When the G omega 0 dB or 1. Okay. So what you should do is omega square 16 equal to 1. Okay. So you simplify this. So you will get omega 4 plus 16 omega square minus 1 equal to 0. So omega is 0.2495. You have 4 answers, so you choose only one that can satisfy these equations. Okay. So that's why you must have the white calculator that can find the roots of 4. Then the phase, okay, is minus 90 degrees. Dua empat 95 divided by 4. So it is minus 93.56 degrees. So the phase margin is 180 minus 93.56 degrees, 86.43. Okay. For question number 2, is you are given a block diagram with DS. Okay. You need to plot. Okay, this one is so 10 as divided by 10 plus 1. Okay, so this one will be cut into 5, 0.2. Okay, so G omega S J omega divided by 10 to 50. Okay, and break frequency is 50 radian per second. Okay, so the question asked, so you need to do the label sketch completely. Okay, so this one you just follow what I did in the class. Okay, okay, phase gain 0 minus 180 degrees. Okay, so you draw one by one. Scan for the 4 decades between 0.1 to 1, 0.1 to 1000, 1000. So meaning that this one is 1, this one is 10, this one is 100. Can. Okay. You draw one by one the factor which is here. So you have two factor. Okay. This one is S. Okay. You have a 4 factor gain, pulse at minus 10 at 10 radian per second, pulse at the origin, and pulse at minus 50. So you have 4. Nevin, can you help me? 20 log 0.2, please. 20 log 0.2. Nevin?
Negative 13.98.
Sorry?
Negative 13.98.
Negative 13.
Yes.
Something like here. Negative 13, eh? Then what do you call that? Pulse at the origin. Macam tu. Okay. What else? 10 zeros at 10. Okay. What else? 50. 50 over here kan? Oh, go down. Macam tu. Okay. So for face DIY, okay, do it yourself by using refer to the formula, refer to the notes that I give and discussion previously. Question 3C is where you are given workload. Here, type 1, third order. So started K equal to 1. Find the gain margin and phase margin here. Plot is given. So first thing, when you have this, you have to draw the straight line. Use a long ruler, 0 decibel. This is the baseline. And minus 180 line. Buat straight line. Can. So, what is the gain margin and phase margin? Abu Bakar Halim. Abu Bakar,
Yes, doctor.
gain margin and phase margin.
One sec. Phase margin.
Okay, so gain margin 16.9 decibel and phase margin 55.64. You have to find the crossover frequency here. Okay, that is your omega GM. So that is your omega PM. Okay. So this is your gain margin. Abu Bakar. Oh, Abu Bakar.
Yes.
Right.
Yes, similar values.
You don't print, that's why you're having difficulties. Okay.
Mm,
Something like this. Okay. Boleh? Can?
Can.
Okay. So Q23C. What else you ask these questions? There is the error of the system to a unit RAM. So there is no is a freestyle and steady state error by observation, boot plot, or calculation. Final value theorem. Can. So since the system is what?
Type 1.
System is type 1. Can. So KV, okay. S to 0. K, yes. But K is equal to 1. Okay. So S dulu cancel 10 1. Okay. KV equal to 1. So therefore the steady state error is 1 over KV equal to 1. Okay. Analyze the stability of the closed loop system. Okay. Stable. Due to positive gain margin and phase margin. Positive. Okay. The final one is gain adjustment. The magnitude needs to be reduced by 30. To increase the range of stability up to the closed system, the gain margin needs to be increased 30 decibel. Okay, using the gain adjustment technique, determine the gain K to achieve the requirement. Okay. So we go to the graph here. Abu Bakar.
Yes.
What is the omega phase margin?
Omega. Yeah. The old one.
Yeah, the one that I asked you to measure.
Omega phase margin is around 0.9.
Omega phase margin. No, here. It's here. 3 radian.
3 radian. Yes. Sorry.
Radian.
Omega GM. Sorry.
At 3 radian, how many decibel here?
Around negative 16.
That is our negative 16, negative 17. Okay, right. So this is your 0 dB. So the gain margin is here. Kan? Gain margin is 17 decibel. Okay. So the question asks, the gain margin needs to be increased to 30 decibel. Okay, what do you mean by that? What do you mean by that? Sorry. The existing gain margin, Abu Bakar, was plus
17.
17 decibel, all right?
Yes.
The targeted gain margin is
30.
plus 30 decibel, correct? So the difference is 30 minus 17, kam haza?
13.
Huh?
13.
13 decibel. And so that's why the gain shift, the gain curve need to be shift up or shift down.
Shift up 13.
Huh? Shift up or shift down?
Shift up.
Astaghfirullahalazim. You don't understand the concept. So here is 17 decibel, right? Okay.
Mhm. Yes.
So the targeted uh, gain margin will be
30.
30 decibel.
Mm.
Okay. So that's why you need to shift down, am I right? Because
Correct.
50 decibel, the curve must be go down, am I right?
Mm.
Something like this, the orange color. Right?
Mhm.
My hand drawing not very beautiful. Okay. Something like this, eh? Like this. So need to shift down in the amount of 13 decibel. Am I right? Shift down minus 13 decibel. Okay? Okay. Miss Lee, tidur ke?
Okay.
Sesan dB minus. Correct. K equal to Miss Lee?
0.22.
0.22. Shift down, eh? It's not shift up, eh? Abu Bakar. Anta fahimta?
Yes, fahim.
Okay. If you shift up, the gain margin will be smaller. If you shift down, the gain margin will be bigger. Kan?
Kan.
What time? Okay, half an hour. Nevin. Oh, Nevin.
Is that
Question 4, please. Can you read question 4?
describe the importance of limitation, if any, of the gain adjustment technique, lag compensator and late compensator. The migratory system can be represented with a unity feedback system as shown in figure Q4b with the system transfer function GS 1 over S plus 2, S plus 5, S plus 7. The bot plot of the open loop system with K equals to 1 is given in figure Q4b Roman 2. To improve the closed loop system performance, the system is required to operate with a 15% overshoot and steady state error of at most 0.1. The position constant Kp is more than 10 to a unit step input. Design a controller in the frequency domain according to the following procedure and find the appropriate control parameter. Provide your comment on the stability of the original system. Design a controller and determine K using the gain adjustment method to achieve the required overshoot. Investigate whether the required steady state error or Kp has been achieved. Design a lag compensator to achieve the desired Kp and maintain the overshoot achieved in the previous design. The lag compensator should be drawn on the board plot.
Okay, so this is the board plot given. I think your final exam will follow this format lah. Okay, part A, part B. Part A, Q1, 2, 3, compulsory. Part B is where you have to choose either 4 or 5. Okay, let's do question number 4. This is theory. Describe the importance and limitations of the gain adjustment technique, lag compensator, lead compensator. That one you can find from the notes. Okay, please refer to the notes. Okay. B, mechatronic system can be represented by this. Okay, third order. Type 0. Okay. The bob load is given by K equal to 1. To improve the closed instead, the required is to operate with 50% overshoot and steady state error 0.1. Okay. Position constant. Design and control in the frequency domain according to the following procedure. So how to do it? Evan, how to do it? Okay. Spec design, Nevin.
Uh, 15% overshoot, steady state error less than 0.1,
Less than,
0.1,
meaning that KP is greater
more
than,
than 10.
okay. Then gain adjustment. Okay. So provide your comment in the stability of the original system. Okay, by looking at the graph here. Okay. Zero dB. Minus 180 degrees line. Okay. So by looking at it, is it stable or not stable? Lee, is it stable or not stable?
Stable. Because phase margin and gain margin will be positive.
Salah tu.
Oh, salah. Huh? It's not stable ah?
Wait. I think your answer not accurate lah. Okay. By looking at this,
Or is it, should the answer be
only
the
you
poles
can
at the left
you can
of
find
the...
only omega PM, am I right?
Yes.
And then omega PM will give you the magnitude negative. Okay? Here,
Uh-huh.
negative. So meaning that that is the reason, only reason why it is stable. The
Oh,
omega
okay.
DM is not available, it's not exist. The gain curve
Oh,
is
okay.
cut at 0 dB at all. So only phase,
Understood.
only phase. So the answer now is the B. The closed loop system is stable as the magnitude is negative at omega PM at omega PM phase angle minus 180 degrees. Okay. So now we draw, we design the compensator, okay, which is OS 15%, which will give you zeta 0.51. Zeta 0.51 will give you phase margin 52 degrees. So that's why phase angle which is 180 degrees minus 52 degrees, 128 degrees. Okay. So at phase 128 degrees, omega is 3.8 radian per second. And the magnitude is minus 46.6 decibel. Okay. Therefore, new gain of 46.6 decibel is required to obtain phase margin 52 degrees. Okay. So therefore, log K is equal to 46.6. K equal to 213.8. Okay. So if you look at the gain, okay, which is 9.7. So the new KP is 20 log KP 9.7. KP is 3.05. Okay. Then using a final value theorem, KP is equal to limit S to 0 to 3.8 divided by 257, which is same 3.05. Okay. Therefore, the required KP is not achieved. Okay. That's why we have to move to habis pula. Okay. We have to move to part 3. Okay. So that using a lag compensator, so that we can achieve the desired KP and maintain the overshoot achieved in the previous design. Okay. Using lag compensator. We know that is the limitation of the gain adjustment. We cannot achieve the KP. Okay. So to obtain, because we must obtain KP equal or greater than 10. But the one that we get is KP is equal to 3.05. Okay. So not good enough. Okay. That's why we left gain adjustment. We go to part 3. We design a lag compensator. Okay. So to obtain KP is equal to 10, which will give you the ESS 0.1. So KP limit S to 0, K to 57 equal to 10. So from there, we obtain the gain K 70 multiplied by 10, which is 700. Okay. 20 log 700, which is equal to 56.9 decibel. Okay, so the magnitude need to be shift up by the amount of 56.9 decibel at the frequency omega 3.8 radian per second. At omega 3.8 radian per second, the magnitude will be minus 46.7 decibel plus 56.9 decibel, which is equal to 10.2 decibel. Okay. So we need to design a lag compensator. Okay, so that the gain crossover frequency occurred at omega 3.8 radian per second. Okay, so that's why we draw the at the work plot. Okay, 0 dB. Okay, so this is your 3.8. This is your 0.38, the ZC. Okay. And then so is minus 10.2. Okay. Okay, we begin from here. Okay. So that is your ZC. Then minus 20 dB per decade, straight line. And this is your PC, which is a 0.15 per decade. Okay. So that's why the lag compensator is G lag S is equal to 0.39 S plus 0.38 S plus 0.15. Okay. That will give you the phase margin, the targeted phase margin. Okay. It's 12:50. So you want to proceed with the question 5 for one? Okay, eh? Can eh? Okay. One Fares. One Fares.
Yes, Doctor.
Can you help me read question number 5, the last one? This one we go fast. Please, question 5.
What is the difference between lag and lead compensator in frequency response? An open loop transfer function with k equals to 1 is given as gs k over s times s plus 1. The work plot of the open loop transfer function is shown in figure Q.5b. Based on the margin values obtained from the plot provided, what can you say about the stability of the system? Using the frequency domain technique, design a compensator GCS so that the system will have the static velocity error constant KV equals 50 second minus -1. Phase margin 50 degrees and phase margin GM about 8 decibels. Design the compensator on the given board plot, submit it together with your answer script. Make the necessary adjustment on the board plot so that the new KV is achieved. Find the new compensated gain K and give the complete transfer function of the compensated open loop system. Sketch the plot of the compensator GCS that you proposed.
Thank you. All right, so this one, difference, okay, lead and lag. So I did the notes, but we can have a short discussion here. CO. Okay. Number one, lag compensator to improve ESS. Lead to improve transient. Can lag compensator ZC greater than PC. This one ZC less than PC. Okay. This is some simple one and the detail you can find from the book Okay. Plot given here. Okay. For question 5. So gain margin. Infinity not available. Phase margin. Phase margin is 51.8 degrees. Okay. So is it stable? Stable. Due to positive phase margin. Okay. Okay, this one is the lead compensator. Okay. For the lead compensator, okay, KV is 50. Okay, phase margin is 50 degrees. Gain margin is 8 dB. That is the requirement. Okay, the requirement of the spec design. Okay. Lead compensator KV 50, phase margin 50 degrees. Gain margin is 8 decibel. Okay. So we use the KV equation, final value theorem. Okay. Which is S KGS, okay, which is equal to 50. Okay. So when you simplify it, you will get K equal to 50. Okay, simplify. Gain adjustment. Or K equal to 50 is 20 log K. 20 log 50 34 decibel. Okay. So new phase margin is 8 degrees. Gain margin not available. This one is the from both plot given. Okay. So you have to do some adjustment, which is additional correction. Which is phase margin equal to 50 minus 8 about 40, 42. So the correction factor is between 5 to 12 degrees. Okay, so you can use 10 or whatever. So let choose correction factor as 6 degrees. So therefore your requirement will be, okay, required is 42 plus 6 degrees, which is 48 degrees. Okay. So some of the class they teach 10 degrees, 6 degrees is between 5 to 12. Okay, it's up to you because design where you can choose your correction factor by your own between 5 to 12 degrees. So sine, okay, sine phase margin 1 minus beta, 1 plus beta. Sine 48 degrees, this one, is equal to 1 minus beta, 1 plus beta, which is beta equal to 0.15. You can simplify later. Okay, I give you the answer. And then j omega 1 over square root beta, which is 2.58. And we have a log 20 log 20 log 2.58. So you will get 8.24 decibel. Okay. To make magnitude 0, equal to 0, after compensation, or compensated, so magnitude, you make it negative, as I teach you in the class, kan? Minus 8.24 at omega 11.4 radian per second. Okay, or we known as omega max 11.4. Okay, so omega max is equal to ZC square root beta. So ZC you will get 4.415, and PC using the formula at the attachment of the exam paper, square root beta, you will get 29.4. Okay, so therefore your G lit will be 29.4 divided by 4.415 S plus 4.415. S plus 29.4. Okay. So this one is, if you simplify, 6.66. Okay. So number 3 is find the new compensator gain. Meaning K overall. So K overall is the one that you get, 6.66. Multiply the existing. The existing is from the transfer function, I think. Where is it? The K that you get just now. K50. Okay, 50. Multiply by 50. Okay, so this is the overall gain, which you can simplify, and then this one is add the boot plot. Okay, something like that. Okay, this is your ZC. ZC is, sorry, this is your PC. PC, which is 29.4. Okay, you draw this at your book load. Okay, ZC 4.415. Okay, so this one is 0 dB. Okay, I think that's all, guys. For this revision, is a very long day. So I hope you can watch again the video. Okay, I will upload in the YouTube. Thank you very much for your attention. I will share again. Tomorrow I will be online again, but different set of question. Then I will share the tomorrow and the today YouTube link. Is it okay?
Okay.
Okay, Doctor.
Okay.
Okay. Thank you, Doctor.
So get ready for the presentation. Thank you very much. Assalamualaikum.
Thank you, Doctor.
Good afternoon.
Waalaikumsalam.
Thank you, Doctor.
Thank you, Doctor.